So tonight I want to have a little chat about a project I recently started on the online optimization of robotic walking assistance for impaired users. And as you probably guessed, this is again about human-in-the-loop optimization. And we were really motivated by the interesting results that some of you guys achieved there. And what I found particularly interesting is the wealth of information that comes in that single physiological signal that is dependent on many interesting underlying processes during locomotion. And what we've seen is that an ankle or a hip exoskeleton or exosuit can effectively reduce the metabolic cost of walking for healthy participants. And I wanted to transfer this concept to assist people following, for example, stroke or spinal cord injury, or people with muscle dystrophy, to assist those people during walking with an exoskeleton. And that probably means changing the type of robot, but it also means taking even one more step back and reconsidering the target metric that we want to optimize. So we've seen that economy is a very powerful metric, but as also the previous speaker argued, there might be different factors that we need to consider on top. And I would argue that these are probably gait speed and gait quality. And the rationale behind this is that economy, for example, can be associated to an increased activity level in our target population, but increased speed, for example, is associated with improved functional mobility and improved gait quality with a reduced risk of falling. And the overarching thought here is that by optimizing those three parameters, we might in the end move towards a direction where we in fact optimizing the health-related quality of life. So for the practical implementation, we used a robot that was developed in our lab, which is a mostly soft exosuit called the MyoSuit, which actively assists hip and knee extension and passively assists hip flexion. And we took signals from a mobile respirometer and signals from IMUs to optimize that in an external PC. And the set we optimized was 4-dimensional for both legs, the force level, so how hard we pull on those cables, and the release point, because our robot works in a way that at some point during stance phase, the forces are driven to zero, that the person can by themselves initiate limb advancement. And that release point can be either early or late during stance phase. So what we wanted to check here is if actually varying those control parameters results in a consistent and meaningful change in our subjects. And for that, we started with a system verification in unimpaired users during uphill walking on a treadmill. And what we found is that we get a very consistent metabolic landscape here. And I want to stress that these are 26 randomly tested conditions, so there's no order, but we still get a very, say, smooth landscape in a way. And we see variations of approximately 10% from our zero force reference condition, which is that dot right here, in our calibration point, so no shift in release, and at zero force. And that was promising, so we wanted to make a move from unimpaired users to our actual target population and see if we could actually optimize their performance in that landscape. So here we see our test with an impaired user with muscle dystrophy walking outside. And here we see his metabolic landscape. And you might realize that there's only 3 dots in this graph and not 26. And that is because after 3 conditions, and that was still while we were building our prior, the participant fatigued. And for us, that brought up some issues that we are working on right now as I speak here. Because we might need to consider longer optimization protocols. So this was a single day. We might be looking into several days for the future. And we might also try to incorporate more prior knowledge and not just start from a flat prior for every person. So as a quick wrap up, we have thought about an adapted target function for impaired users. We have verified our framework for functionality and tests with unimpaired participants. And we have started to explore the challenges specific to our target population in the use with our MyoSuit wearable robot, and will continue to do so in the coming month. Thank you. scenarios. The first person was walking on a relatively steep ascent, 10 degrees uphill at 1.25 meters per second. And this was intentional to have a loading situation where we would expect to see big differences for the type of assistance we provided. And the second person was walking slowly. So we are looking at, say, 3 to 4 watts per kilogram in the second case, and more like 14 to 18 in the first case.
So, can you run like the proportionality between them? I mean,
so let me just go back here.
Red and blue are nice, but
so, what is the question specifically about?
just can you give us some sense of how to compare? I mean, red and blue is one thing, but 16 to 14 and
Right.
4 to 3 is another.
So there is no intention of making a comparison between those two people. The first test was to establish that the framework is working, and actually modifying those two control parameters results in a consistent and meaningful change for that person. And the second case was our first attempt to explore using that concept in a participant with muscle dystrophy.
Hi, Jeff Ducray from Unimpaired. So can you go to the next slide?
Sure.
Or the slide with the triangle, I guess. I thought it was.
Slide is a triangle.
Yeah. So it seems like economy and speed are easy to quantify, but how do you propose quantifying quality?
So that is still something we're investigating, but right now I would look into metrics that are indicative of the risk of falling. And that would be variability of parameters such as step width, step length, or stance phase relative to overall stride duration.
I'm sorry, I'm just confused. How you generate your object functions through this array?
The object function for this?
Yes.
Well, this right now doesn't exist, to be honest. So this objective function is something that is fairly high level right now. And for the future, I anticipate it to be something where we are working with subjectively chosen weights between those 3 dimensions. And it will also be somewhat related to the optimization function we end up with in the end, such that they're well matched in terms of convergence properties, for example.
One quick one. Back here.
How long did the participant in the clinical participant walk before fatigue?
He walked 6 minutes, like 5-minute warm-up, then 6 minutes experimental conditions, and then he fatigued.
With how much break in between?
There was a 2-minute break in between every experimental condition, but no break before the first experimental condition after warm-up.
Thank you, speakers.